Hello everyone, welcome to a live stream of Chemistry 223. My name is Travis and I'll be helping you through this live stream today. Today we're going to talk about thermodynamic properties in chemistry, mainly the Gibbs free energy and entropy and finding the equilibrium constant using Gibbs free energy. But first, as always, I'm going to post a few links in our chat window. So I got links to the Learning Center's webpage as well as their Facebook and Instagram. Follow them on Facebook and Instagram to get up-to-date notifications whenever we make new resources available and stuff like that. We also have a YouTube channel where we post various videos on student success and other resources we have there. This YouTube channel is a playlist of all the videos I'm making here for Chemistry 223. So check those out if you ever have to look back on some concept that you're not quite understanding it. And you can also find playlists for 221 and 222 as well that I've done over this summer. So give those a check and give those a view and like them if you enjoy them. Today, let's get started on problem 6 here. In this figure below, which is 16.8 out of the OpenStax textbook, all possible distributions and microstates are shown for 4 different particles shared between 2 boxes. Determine the entropy of change, delta S, if the particles are initially evenly distributed between 2 boxes, but upon redistribution, all end up in box B. So box B is this one up here. And they say at first they're all evenly distributed amongst those boxes. So if they're evenly distributed, it's basically going to look like part C right there, where we have 2 particles in each box, and these are all the different configurations that those particles could be in, or positions that could be in. That's each of these parts A, B, C, D, and E are basically a macro state. And each macrostate contains several microstates. And if we count up all those microstates, we can find out what number of microstates there are. So in this case, if we count those, there's 1 in this column, 4 in that row, 4 in this row, 6 in this row, 4 in that row, and 1 in that row. Adding those up, I get 16 total microstates. So when we are talking about the change in entropy, if things are allocated in, say, for part B, it would have 4 out of that 16. For part C, where we started out at, it would be more of a 16 out of, or 6 out of 16, that type of ratio. Now we can determine basically that's the number of microstates divided by the total macrostates that were involved there. Now to find the change in entropy, the delta S, we can use the equation, which delta S is equal to KB. That's the Boltzmann constant. And I'll put a little note here, KB is equal to 1.38 times 10 to the negative 23. The units on that are joules per Kelvin, which is a standard unit of entropy. So delta S is equal to the Boltzmann constant times the natural log of, call it W. And W is the different number of microstates that we have there, essentially. What microstates that has in relation to the whole. So we can calculate the change, because it's really, this is really S. The change in S would be S final minus S initial, which is my delta S. And we can solve that by basically saying KB, the natural log of W final minus the Boltzmann constant times the natural log of W initial. And then using the laws of logarithms, we can actually combine those into one logarithmic rule. This is equal to the Boltzmann constant times the natural log of the ratio. It's always going to be F final over F W initial. And that'll tell us basically the change in entropy, S. So now we can plug those in where those W values are basically my 4 over 16 and 6 over 16. In this case, 4 and 6, because those will cancel each other out. This is going to equal KB natural log 4/6, which is really the Boltzmann constant, just to simplify, of 2/3. Now, based on the logarithmic graph and how the logarithms work, taking the logarithm of a value that's less than 1 is going to result in a negative number. So we can already see the sign of this is going to end up being negative. So if I plug this now into my calculator, where is my calculator? Pull it up here. That'll be 1.38 times 10 to the negative 23 times the natural log of 2 divided by 3, 2/3. That's going to equal a negative 5.5, let's call it 5.60 times 10 to the negative 24. And that's the units of joules per Kelvin. So that's going to be my change in entropy. It's a very slight change in entropy, essentially, because you're going from 4 states to 6 states there. Or 6 states to 4 states. And it's going negative because it's actually getting less chaotic. Going from this state here to that state there, it's shrinking the possible number of states that it can be in from 6 to 4, because we're looking at things specifically in that type of configuration for B. So that's why it's a negative entropy. If it was more spread out, it had more chaos involved with it, essentially, more microstates possible, then it would be a higher entropy, and we'd expect a positive change in entropy. All right, let's go on to number 14, which is also dealing with entropy. And this one, it's a bit more of a conceptual problem here. We want to consider the two processes, sublimation of I2 solid and melting of I2 solid. So that's I2, which is iodine, like diiodine, a solid form at room temperature for the most part. It can sublimate into a gas, which is just transfers straight to a gas, skipping the liquid phase, or it can go from a solid phase into a liquid phase, depending on the temperature that's involved with it. So what I want to know, is the change in entropy positive or negative in these processes? In which of those processes will the magnitude of entropy change be greater? So I'm going to rewrite these just so I can make comments below them. I2 solid is forming into I2 gas. So in this situation, the gas molecules, gaseous I2, they're going to have a lot more space for these molecules to move around in. The solid are kind of rigidly stuck in one small space, where the gas is floating and all the molecules are moving around constantly. So that increase in possible microstates essentially will increase the entropy that is possible for that. So has more possible. Say locations, therefore more microstates. If it has more microstates, that means, say, thus an increase in entropy. Therefore, the delta S is going to be positive, is basically what I'm saying. We're going to have a positive delta S when we're going from a solid to a gaseous state. Now, if we look at I2 solid just melting into I2 liquid, so if we remember, a solid is kind of confined to a specific area. It's like this is the volume of the solid. When it turns into a gas, it fills whatever space and container that it's in. Now, when it's a liquid, it kind of fills the bottom edge of that container. Gravity's still pulling it down, so it's not floating up into the air. It's bound by its intermolecular forces still, and it just kind of fills that bottom surface of the volume that it's in. So it definitely still has, so I'll say liquid, should do a nice purple color. Liquid still has more possible locations for the molecules. So it can still spread out more, so it's going to have more possible microstates as well. So therefore, more microstates are possible. Thus, an increase in entropy. So again, we have this increase in entropy for both of these cases. So I would say delta S is still going to be positive for that one, because we're going from a solid state to a liquid state. It's going to have more entropy involved with that transformation. As far as which one is going to be the greater magnitude, since the gas has more possible locations for these molecules to float around in, more microstates are going to be possible for that. And those more microstates are going to allow for a greater increase in entropy. So the magnitude of the the transference into gas from a solid is going to be greater than the magnitude of the transference of a solid to a liquid. So in part 17 here, the number 17, we want to predict the sign of the entropy change for the following processes, and we want to give a reason for that prediction. So we have three different ones here, A, B, C, and in the first one, we have sodium chloride. So I'll just write that out. Na plus aqueous plus chloride aqueous is producing NaCl solid. So we have a precipitation reaction basically happening in this case. We want to know what's the entropy involved with this. And one of the signs of a change in entropy is looking at how many moles of product versus the moles of reactant that you have. So in this case, we have 1 mole of sodium ions floating around in the solution. We have 1 mole of chloride ions floating around in solution, and they precipitate into 1 mole of sodium chloride. So since we're going from 2 moles to 1 mole, I'm going to say that's going to be most likely a reduction in entropy. We have less entropy in this state in the product than we do in the reactant. So that would mean the delta S is a negative value. For part B, we have 2 iron solid plus 3/2 O2 gas, and that is forming into Fe2O2 solid. So again, we're looking at the same type of transformation where we go from, say, 3.5 moles of reactant forming into 1 mole of product. And that reduction in moles is going to cause a reduction in entropy as well. So the delta S for this one is also going to be a negative value. It's also going from, our iron is going from a solid, but our O2 gas is going from a gas into a solid. So it's sucking down all those possible states that it could be in into a much more compact area. You can say something similar for part A. We had aqueous chloride and sodium floating around in a solution. Now, I don't know what that volume was, but there was some volume of solution. And either way, that volume is going to be condensed dramatically when they're now stuck into a solid form. So those ions are now fixed in a much more rigid form to it. So its entropy is going to be obviously it's going to be reduced in that way, much smaller than it was before. Looking at part C. So this one is 2C6H14. That'll be hexane, I believe. It's a liquid hexane plus 19O2 gas. And that's going to produce 14 H2O gas plus 12 CO2 gas. So in this case, we can count up that mole to mole ratio that I've been talking about. We have 2 plus 19 is 21 moles of reactants, and 14 plus 20, that's 20, or 14 plus 12 is 26 moles of product. So you can see we have an increase in moles, which means we're going to have an increase in entropy there. So the delta S is going to be a positive value for that, just because we have more moles of product than we had of reactant. So there's going to be that change, that positive change in delta S. For number 18 here, we have to write a balanced chemical equation for the combustion of methane. Let's do that first. Methane is CH4 here. So that's going to be CH4 gas plus, and for combustion, we're always reacting it with O2 gas. Oxygen is going to form, and then it says it's going to give carbon dioxide and water vapor. So that'll be CO2 gas plus H2O gas. And they want us to explain why it's difficult to predict whether delta S is positive or negative. So the difficulty starts to come when we look at kind of the standard things that we look at when we're trying to predict what that entropy change is. If we want to see them changing state from a solid to a liquid, or a solid to a gas, or a liquid to a gas, we know there's going to be an increase in entropy involved there. But in this case, everything stays a gas, so it's hard to tell on that regard. If we look at our mole to mole ratio, we have 2 moles of reactant forming 2 moles. And I don't think I balanced my equation here, did I? No, I need 2 of that and 2 of that, I believe. Yeah, now I have 1 carbon on each side, 4 hydrogens on each side, and 4 oxygens on each side. Cool. So let me recount my moles. So now I have 3 moles of product, and I have 3 moles of, 3 moles of reactant, 3 moles of product. So my mole to mole ratio is the same. So I'm not increasing the number of atoms there are in the existence, and I'm not changing the state of anything. So it really comes down to the formation of those things, whether or not the delta S's, or the change in entropy, is going to be equal to or greater than for one or the other, and that's harder to predict. So those are the common indicators I look for these types of things. Number 26 is my next one. Sorry, it's from the following information, I want to determine the delta S. So this is the standard entropy of change for the following. So here they give us the basic equations for them, and they want us to find what that delta S is. And we can do that by looking up what these values are going to be in the appendix. And a lot of these values are going to be tabulated for us, essentially. And we can look up what the change in reactants, the standard change for the reactants and the standard change for the products, and we do the products minus the reactants, or the sum of the products minus the sum of the reactants. So I'm going to switch over here to my appendix. This is Appendix G in the OpenStax textbook online, and I'm going to look for these values here. We're going to start off with part A. Part A is N gas plus O oxygen gas. Notice it's O1, not O2. Oops. Switch back to here while I'm writing. Is producing NO gas. So I want to look for those values: nitrogen, oxygen, and NO gas. So switching back now. And see, I can make this maybe a little smaller. And make it easier to read that way. There we go. So pulling up, I've highlighted a few of these that we're going to use today. Maybe some that I used previously on there too. There's nitrogen gas. Oh, we're looking at there's 3 different values on here: the delta H, the delta G, and S. So S is what we're looking for, that rightmost column. Going back down to my N gas. Don't grab the N2 by mistake in this one. We want that N gas is going to be a 153.3, and the units for that should be in joules per Kelvin. Joules per Kelvin. Yeah, and they have joules per Kelvin per mole, but since we're multiplying this times 1 mole, we end up with just joules per Kelvin. For oxygen gas, that's going to be this one. I didn't highlight it for some reason. We have 161.1. So 161.1 joules per Kelvin. And for NO, was here at 210.08. Or 0.8. Okay, I'm going to switch back to my... There we are. So I just wrote down what those values were for each of those. And now what I want to do is write the sum of the products minus the sum of the reactants. So in that case, this is going to be 210.8 joules per Kelvin minus 153.3 joules per Kelvin, plus 161.1 joules per Kelvin. So I'm subtracting the sum of the reactants from the product. Those are all the entropies. To find what that change in entropy is. So our calculator will solve this for us. That's 210.8 minus 153.3 plus 161.1. And I put that parenthesis in there to make sure I'm subtracting both of those values. This gives us a negative 103.6 joules per Kelvin. And that is going to be our delta S. Move all this stuff up just a little bit. Oh, and now let's do the same thing for part B. For part B, we have N2 gas plus O2 gas. It's going to create 2 moles of NO gas. So looking at this first one real quick, we can see that we had 1 mole here and there was 2 moles of reactant, and we see that value ended up being a negative number. Because our change in entropy, we had a reduction in the number of moles, so and that value ended up being negative, and that's exactly what we wanted to see. For this next one here, we want to look at, well, what is the entropy of formation for N2 gas. So let's switch back over here. N2 gas is going to be this one up here, and the entropy is 191. That's 191.6. O2 gas going down. Did I pass it? I might have passed it. Go back up. There it is. O2 gas. That's 205.2. And then NO gas, well, we had that up top. That's 210.8. And those are all in joules per Kelvin. All right, so now we can take our products. I switch back. Take our products minus our reactants. So in this case, we had 2 moles of NO. So you have to do 2 times 210.8 joules per Kelvin minus, I'll put my parentheses, and then I have 1 mole of N2 gas plus 1 mole of oxygen gas. And there we go. Yeah, we can just do the math, that's 210.8 minus 191.6 plus 205.2. It's going to be 24.8 joules per Kelvin. So you can see that's the general philosophy on how we want to do things. Make sure we get this products minus the reactants. We've got 2 more to do here, so let's knock them out pretty quickly. The next one, part C, is going to be N2 gas, which is just going to form into 2N gas. So luckily we've already looked up these values. So the N2 gas was 191.6 joules per Kelvin, and the N gas was 153.3 joules Kelvin. Now we can see this goes from 1 mole to 2 moles, so we would expect a positive delta H. Let's see if that works out right. We have 2 times 153.3 minus 191.6. And that's all going to be in joules per Kelvin. So that's 2 times 153.3 minus 191.6. I missed a 1. There we are. That's equal 115.0 joules per Kelvin. And there we go. So that's going to be our positive value, just as we expected. And we can see it's 115 joules per Kelvin when we transfer N2 gas into N gas. For part D, is O2 to O gas. So O2 gas is being transferred into 2O gas. So again, we already have these values that we looked up previously. So we can see O2 gas we had at 205.2 joules per Kelvin, and O gas we had at 161.1. So when I do the math on that, I have 2 times 161.1 joules per Kelvin minus 205.2 joules per Kelvin. So that's 2 times 161.1 minus 205.2. And we end up with 117 joules per Kelvin. Should be a 0.0 for sig figs. And again, we can see that it's a positive number because we went from 1 mole to 2 moles, both in the gaseous state. So we have positive 117.0 joules per Kelvin. So I'm going to start talking about Gibbs free energy. And really, we use Gibbs free energy to determine whether something is spontaneous or not, whether it's going to happen without a lot of encouragement, or whether we really have to heat it up or do a lot of things to it to make that reaction happen. And in this question here, it says a reaction has a delta H of standard change in enthalpy equal to 100 kilojoules per mole and a standard change in entropy of 250 joules per mole Kelvin. Is the reaction spontaneous at room temperature? If not, under what temperature would the conditions be spontaneous? So to find this out, we want to find that delta G of formation. And there are a couple conditions there. If that delta G, or standard change in Gibbs free energy, is greater than 0, we're going to say that that is non-spontaneous. And if that delta G is less than 0, that makes it spontaneous. Aeneos. So the equation for this is that delta G is equal to delta H minus the temperature times delta S. So it's the enthalpy minus the entropy times temperature. And that temperature is in Kelvin. So in this case, they're telling us that room temperature is 25 degrees C, which is equal to 298.15 Kelvin. Because 0 degrees C is equal to 273.15 Kelvin. So we just add 25 to that. So that's equal to our temperature. And they're telling us what our delta S is here and our delta H is there. So we can plug in and say that delta G is equal to, say, 100 kilojoules per mole minus the temperature, which was 298.15 Kelvin, multiplied by 250 joules per mole Kelvin. We can see here the kelvins are going to cancel out. One thing to note is that we have kilojoules on this term and joules on that term. So we don't want to straight subtract those just yet. I want to make sure I write this one instead as 100,000 joules per mole. And now I can actually do the math because I have the same units on both sides of it. So that's 100,000 minus, that's 298.15 times 250, which is going to equal 25462.5 joules per mole. If we want to write that in kilojoules, just moving that decimal place 3 to the left, 25 point, we're at 3 sig figs, so I can say 5 joules per mole. There we go. So that is a positive number, right? So that's going to fall in this range. It is not spontaneous. So how do we make it spontaneous? Well, we want to find out at what temperature it's going to reach 0. So one thing I like to point out is this graph down here, this little chart. Let's see if we can move it. Yoink. So in this chart, what we have is it's the Gibbs free energy on the left side and the increasing temperature on the right side. And based on this equation, and I'll rewrite it here, delta G is equal to delta H minus T delta S. Based on that equation, we can see how the relationships of delta H, the change in enthalpy, and the change in entropy affect the change in Gibbs free energy. So let's start at the bottom of this, if both of these values, if delta H is a negative value, delta S is a positive value, we have a negative here and a positive value there, but that positive value is being subtracted. So the total here, Gibbs free energy, is always going to be negative if these conditions are true. And if it's always negative, that means it's always spontaneous. Now we can look at these conditions here. If delta H is a negative number, right, which means that's good, that's helping that Gibbs free energy be spontaneous, but delta S is also a negative number. Okay, negative times this negative is going to be a positive number, and therefore this term will be positive and this term will be negative. So as long as delta H is greater than the product of temperature and delta S, we're fine because we're still going to have that negative number. We're still going to be in this realm being spontaneous. But at a certain point, we're going to cross that threshold as the temperature rises, where the temperature times the change in entropy is going to be greater than the change in enthalpy, at what point we're going to enter a positive non-spontaneous Gibbs free energy. That's basically following this line up here as we cross this threshold. Now, a similar thing is true if we end up with a positive delta H and a positive delta S. So with a positive value here for enthalpy and a positive value for entropy, this entropy value is going to be subtracted from that. So when this term becomes greater than this term, we're going to end up crossing down into this spontaneous realm. Now, if the delta H is going to be positive and the delta S is going to be negative, this negative times a negative is going to be a positive. You're going to have a positive plus a positive, and you're going to end up with a positive Gibbs free energy all the time, which means it's non-spontaneous. So to answer the second part of the question, we really want to find out, when is Gibbs free energy equal to 0? When does that happen? When do we cross this threshold right here? At what temperature? So that is going to happen, and we know these delta H values at 100,000 joules per mole minus the temperature times 250 joules per mole Kelvin. So we want to find out what that temperature is going to be. So we have to do a little bit of algebra. I'm actually going to shrink my graph down. Let's just get rid of it for the time being. I need a little space to work. So mathematically, since we have 0 on this side, we can split things up and say it's T times 250 joules per mole Kelvin is going to equal 100,000 joules per mole. And then all we have to do is really divide by 250 joules per mole Kelvin. And when we do that, we're going to cancel out my joules and my moles. We're going to end up with Kelvin up on the top. Let's cross that out down there and write it up top. And it's really going to be the temperature is equal to 100,000 divided by 250, which is equal to 400 Kelvin. So when the temperature is at 400 Kelvin, I lost my graph. We are crossing that threshold where the Gibbs free energy is. So anything greater than that, I should really write the temperature should be greater than 400 degrees Kelvin. It's at 0. It's not quite spontaneous. It's not quite non-spontaneous. And nothing's really going to stay right at 0. It's going to flicker, right? But anytime it's greater than 401 and so on, we can expect a more spontaneous reaction. And the greater the temperature, the faster that reaction is going to happen. So let's go on to number 34. And in this one, we're going to use the standard free energy in appendix G. That's that same appendix I showed you, but now we're looking at the middle column. Hop back over there. So again, appendix G, and we're looking at this delta G right there. The standard free energy of formation. We're looking for this middle column, and we want to determine, we're going to use those values to determine the free energy change for each of the following reactions, which are run under standard state conditions and 25 degrees Celsius. Identify each as either spontaneous or non-spontaneous based on these conditions. So really find the delta G of formation and determine, is this going to be spontaneous or not? So for part A, we have carbon. Well, carbon has different forms. There's graphene, there's graphite, there's diamond, depending on the pressures that it's been put under. In this case, we're looking at graphite. And graphite's probably the most common version of it. It's definitely called the lowest energy state to a large degree. And a lot of times, if you were to look up an entropy for that, it would actually be 0, I believe, because that's going to be your elemental carbon, essentially. Can't find carbon on that list. There it is. Oh no, for this one, for Gibbs free energy, that baseline is 0 because we have elemental carbon. And we can see that in my window here. You can see diamond below that has a change in Gibbs free energy of formation greater than 0 because it actually takes energy to put that in there. But here we have 0 in this regard. So we're going to add to that O2 gas. And I forgot what O2 was off the top of my head, so we can scroll down and look, scroll up maybe, do a search for oxygen. There it is. Oxygen, oh, of course, O2 gas is also elemental. So we had 0 and 0 for those. So those are going to form into, to create, what does it say? CO2 gas. So let's look for CO2 gas on here. There we are. And we're looking at negative 394.36. 394.36. Switching back now. And the units for that should be joules per Kelvin. Oh, sorry, it's just kilojoules. These are in kilojoules. So when we do our products minus reactants, in this case, our reactants are all elemental, so they're 0. So this value here is going to be equal to the change in Gibbs. Now, to answer, identify whether it's spontaneous or non-spontaneous, it's a negative number, so this is going to be spontaneous. So for part B, we have O2 gas plus N2 gas. And it's forming 2NO gas. Now, this is still going to be 0, and that's 0. We have elemental nitrogen, N2 gas, elemental oxygen, O2 gas, and now we have NO gas. We looked at NO gas when we were talking about entropy, but what is the Gibbs free energy value for that? I'm just going to look it up real quick. This says 87.6 kilojoules per mole. So now when we do the math on that, we really want to do the sum of the products minus the sum of the reactants. So that's going to be 2 times 87.6 kilojoules. And then it'll be minus 0 is equal to 87.6. That's equal to 175.2 kilojoules. That's going to be a positive number. Since it's a positive number, that means it's non-spontaneous. For part C, we have 2 of copper solid plus sulfur gas is producing copper sulfide. There we go. And it must be a copper 2 or copper 1 plus. So in this case, and that's a solid, we can see that we have a solid and a gas. You have 3 total moles of reactants going down to 1 mole of reactant there. And we can look up those values. Elemental copper, that's going to be 0. Sulfur is also, I think, going to be 0. Oh, it's not. Because sulfur gas is not the smallest state. And we can see, there it is. Switching over to my window. It's 238.25. There we are. So that's 2 238.25 kilojoules. And then copper 2 or copper 1 sulfide. We would look at copper C. Find Cu2. There it is. We're at negative 86.2 kilojoules. So we can solve that just by taking that negative 86.2. I'm going to subtract from that 238.25 kilojoules. And since we're subtracting from a negative number, we know it's going to be even more negative, essentially. So negative 86.2 minus 238.25. That's equal to negative 324.45. And really, I'd want to break it down into one decimal place and put kilojoules. So that's, again, a negative number, making it spontaneous. That should be a U. Part D is calcium oxide, which is a solid, plus H2O in a liquid form, produces calcium hydroxide. Solid. So I looked these up earlier. This is 603.3 kilojoules. We have negative 237.1 kilojoules and negative 897.5 kilojoules. So to do this, just like before, we do negative 897.5 minus negative 603.3 plus, really, minus a 273. My dyslexia is kicking in. 37.1 is equal to negative 897.5 minus negative 603.3 minus 237.1. That's going to be a negative 57.1 kilojoules per, just kilojoules. My finger doesn't want to grab it. Slide it away. My calculator is possessed. There it goes. Whoop, up. Okay. Hopefully it comes back later. That makes it spontaneous. Spontane, E-O-U-S. Spontane. I can't spell well, so forgive me if my spelling's way off. I know this one's spelled wrong. There we are. Because they're negative numbers, we know we're going to have a spontaneous reaction there. Part E. E is iron 3. Fe2O3 would be iron 3 oxide, solid, plus 3CO gas, carbon monoxide, is going to produce 2 iron solid plus 3 CO2 gas. So the enthalpies for these, the Gibbs free energy for these is negative 742.2 kilojoules. Negative 137.15 kilojoules. Iron solid is its elemental form, so that's 0. And then CO2 is negative 394.36 kilojoules. I'm just looking that up on the table. I just did it previously, and I'm trying to save a little bit of time so you don't have to watch me scroll through everything frantically. So just writing this out real quick, that's negative 394.36 kilojoules minus negative 740. Oh, I should put a 3 because I need to multiply that value by 3 because we have a stoichiometric ratio there of 3, or stoichiometric coefficient. Plus 3 times negative 137.15. So now you have 3 times negative 394.36 minus negative 742.2 plus 3 times negative 137.15. So that's going to equal a negative 29.43 kilojoules, which is going to be a negative value, so it's spontaneous. This next one, number 40, we want to calculate the Gibbs free energy, the change in Gibbs free energies for each of the following reactions from the equilibrium constant and the temperature given. So to do this, we use this equation here where that delta G is really equal to negative RT ln of K, where K is that equilibrium constant. And sorry, that should have a little whoop. And R in this case is equal to the more physics version of R in joules. So that would be 8.314 joules per mole Kelvin. The one we use for the gas law is really just in atmospheres and liters instead, because a pressure times a volume is going to give you energy. So in this case, we have joules per mole Kelvin for R, and we can then use that to calculate it. I'm not going to do all of these. I'm going to skip a few just for time. So let's go ahead and redact a few that we don't want to deal with right now, just for the sake of time. One more. Let's pull this one out. And let's slam through those 3 there. So for part A, I have Cl2 gas plus Br2 gas. It's producing 2BrCl gas. And really what we need to focus on is the temperature and that constant. So the temperature is going to be equal to 25 degrees Celsius, which is equal to 298.15 Kelvin. That's 25 degrees Celsius, or 25 plus 273.15, which is what 0 degrees Celsius is in Kelvin. So if that's our temperature and we have an R value there, we just need to know that K is written up here. K is equal to 4.7 times 10 to the negative 2. So that means we can solve this by delta G is equal to negative 8.314 joules per mole Kelvin times the temperature, 298.15 Kelvin, times the natural log of 4.7 times 10 to the negative 2. Now, with natural logs, again, we can tell if the value inside the natural log function is less than 1, which it is in this case. This is going to be a negative value. Since we start off with a negative value up here as well, and this and this, or temperature always has to be positive when it's in Kelvin, because it's an absolute scale, and then the R value is always going to be positive. It's a constant. So that means that our delta G has to be a positive number. So we can already see that it's non-spontaneous. But what is the value for it? So that's negative 8.314 times 298.15 times the natural log of 4.7 times 10 to the negative 2. And that's equal to 7,579. Pen. Equal to 7,579.3. Or really, and this is going to be in unit wise. See, the Kelvin's going to match out, and that's joules per mole. Or we can say just joules, either way, because you're going to end up, per each mole of compound you have, you're going to have that many joules, is what they're saying. So I'll say just joules per mole. For part B, and I'll avoid writing down the balanced chemical equation for it and just look at my temperature is equal to 500 degrees C, which is equal to 773.15. Just adding 273.15 to that. That's in Kelvin, and my K value is equal to 48.2. So delta G is equal to negative 8.314 joules per mole Kelvin times, in this case it's 773.15 Kelvin times the natural log of 48.2. So it's negative 8.314 times 773.15 times the natural log of 48.2. And that's going to equal negative, that'd be 24911 joules per mole. See, it's a negative number there. That negative number implies it's a spontaneous value. And we can see by the math, since this value here, that K value is greater than 1, we know it's going to be a negative delta G. So just by knowing that K constant, you could determine what that delta G is, because the equation for everything else has to be positive. This has to be a positive number. This is positive. We're throwing a negative in front of everything. So if that K value is greater than 1, we're going to have a positive value at the end, a positive value for this term. If the K value is less than 1, we're going to have a negative value. The last one I'm going to do is part D. Really, it's the same thing. We can already see my temperature is pretty high, but my Kp value is going to be greater than 1. That's 4.9 times 10 to the 2, so it's really 490. So we're going to end up with a positive, or sorry, a negative value there. And we just plug it into that same equation. So it's really just delta G is going to be equal to negative 8.314 joules per mole Kelvin times the temperature was 500 degrees, sorry, 550. So add 270 to that. Which one was that? D. We have a temperature of 823.15 Kelvin times the natural log of 490. .314 times, start that over, 8.314 times 823.15 times the natural log of 490. That's going to be equal to a negative 42392. That's 42,000 joules per mole. Or we can say that as negative 42.4 kilojoules per mole. And it's negative, so it's going to be non-spontaneous. And that was, just to label it, part D. Last one I'm going to do today, because we are already out of time. I'm just going to hit a couple of these, say 2 of them. Let's go with, doesn't really matter which, so let's just do A and B. And that same equation that we used last time can be rearranged. So if I have delta G is equal to negative RT natural log of K, and I want to solve for K, which is ultimately what we want to do here. I want to find that equilibrium constant. We need to move everything but the natural log of K onto one side of the equation, and then take everything, make everything an exponent to E. So in that case, I'm going to divide both sides by RT, which gives me delta G divided by negative RT is equal to the natural log of K. Move that over just a little bit. Missed my little loop. And then I can take both sides to E. So E to the power of both sides of those, essentially. And E to the power of natural log of K is just going to be equal to K. So I can write that as K is equal to E to the power of delta G minus RT. And that's the equation I'm basically going to be using for these values. It's just a rearrangement of what we had before. And here they're giving us the delta G value, and they're saying everything's at 25 degrees Celsius. So all we really have to do is plug and chug at this point. So to start off with this part A, that's negative 10.88 kilojoules. I want to convert that into joules because my R value is equal to 8.314 joules per mole Kelvin. So I need to convert my G, or delta G, into joules. So that's just 880 joules divided by 8.314 joules per mole Kelvin times the temperature, which is 298.15 Kelvin. And now we have that fraction that's the same as this exponent here. And we just take that to the power of E, and we say that's equal to K. I'm going to work my way from that fraction backwards to make it a little easier to write, for one thing. I always end up writing everything too big in the fraction. And then we just have to plug it into our calculator. So grabbing our calculator here, to give it to my E, it's the second of the ln, so I get that E to the exponent. And I do negative 10.880 divided by 8.314 times 298.15. There we go. And that's going to equal 1.24 times 10 to the negative 2. So that's how we can find those K constants based on that. It's really just plugging in the values that they give you into that equation. And it's important to realize that that's really just a rearrangement of this equation we were using previously. And it's all kind of just by a rearrangement of different equations to say that this relationship is equal to this relationship, which is equal to that. And based on that, we can solve for these values. So if we, just like before, if we knew what that K is, we can know that what this what the delta G is, and vice versa. And it's also important to know that since that delta G was, in this case, oh, this should have been a positive. Oops, so a negative of a negative there. So this would be a different value. Whoopsie. Go back up to here. I need to drop this because originally it was a negative, but the equation states that we're taking that value and making it negative. Oops. The little negative sign right there. So I left that out. So that's really going to be 80.6 is my K value. So based on that value, we can see since we had a negative delta G, we have a positive, or we have a K value greater than 1. And that makes sense based on the equations and what we were talking about with how this equation works there and some of these other equations here as well. So either way, that's all I have for you today. Definitely stop in for my drop-in tutoring or make an appointment with me, our chemistry tutor this summer. And if you have any other questions, and have a great day and enjoy the heat.